So I'm an academic. So I'm assistant professor at Georgia Tech. And today what I'm going to talk about is research that we're doing at my group in combining data mining and human-computer interaction techniques to help people make sense of large graphs. So the work that you're going to see, work done by a PhD student at the top, master's student on your right and on your left, and an undergraduate student on your right. And I like to name things after myself. So I call my group the Polo Club of Data Science, and we work with large graphs. And some people call them large network data, right? So many examples they can imagine, like the internet, so which is a 4 billion node graph where each node is a web page and the edges would be web links, and Facebook. 1.7 billion users, the users are the node edges of friendships, and in many other domains like academia, you will have citation network, papers are nodes, edges are citation edges, and you can imagine there are actually many more examples like that, like in Twitter, you have who follows whom, Amazon, who was what, and AT&T cell phone network, who follows whom, right, or who calls whom, or protein-protein interaction in biology. And the kind of scale of data that we work with is in the million to billion scale. So here's a short summary of the kind of the largest graph that we analyze. So largest was the second one. There's a collaboration with Symantec, and we call it machine file graph. So it describes the relation between file and machine. If a machine reported a file, then there's an edge connecting them. So in that graph, we have 37 billion edges, 1 billion nodes, which are either machine or files. And whenever I show this note, I need to make a disclaimer because they say, oh, you only work with large data. Actually, that's not true. So we also work with small data. Actually, it's incredibly important that our techniques work with small graphs. I'm stealing my colleague John Stasko's quote, small data also needs love. So we work with small data as well. So often we try our techniques on small data and then scale that up to a larger data set. But having all these large amount of data, we will say, well, fantastic thing, right? You can do all these exciting things. You can potentially cure disease if you know that protein-protein interaction network. You can figure out the consumer trend, what they're going to buy. You can analyze the Amazon graph example. But there's some fundamental shortcoming, I would say, or problem. Actually, all of us share that, so it's not particular people. There's a shortcoming where it makes it really hard for us to really leverage all these large amount of data. And I would really boil it down to just one single number, number 7. And this number just makes us really not very efficient, not really good at leveraging all these large amount of data. So any short quiz, anyone would say, can guess what that might be? 7, yes? Oh, yes, very good. First trial, yes. The number of things that you can hold in your working memory, right? So the very famous Miller's law. So they did a study back then, but it's actually still true. So there's only a limited number of things that we can hold in our working memory. 7 plus or minus 2, and then we know today is even smaller, right? You use a computer, maybe 5 plus or minus 2 if you're lucky. So what that means is that even though you have access to all these large amount of data, and it doesn't really mean that you can leverage all of it. So what's more important is how to help people boil down all this large amount of information into things that they can really analyze, really process at a time. So which turn to this very familiar slide that you probably have seen 1,000 times, turning data into insight. So everyone can say it. So I also say it. So how do we actually do it? So this is our approach, combining data mining techniques and human-computer interaction techniques. So more specifically, we want to leverage what computer is really good at and also what human beings are really good at, and complementary, combine the best of both worlds. And actually both areas have long been developing methods to help people make sense of large network data, but traditionally or conventionally, there's not as much cross-pollination as you might expect. For example, in data mining, often focus more on automated techniques like summarization, clustering, classification, and so on. And all of them are very scalable, scale to million, billion items. And human-computer interaction, on the other hand, is more user-driven. They care a lot more about the user's goals. It would design novel interaction techniques, visualization techniques, and so on to explore the data. And because often they are more manual in nature, so they're less scalable. So how do we combine them, right? So I'm going to show you a quick example, simplified example. So let's say you're working in a telecommunication company and your boss said, oh, so we have collected all this data on customer, and the note in the graph are customers, and if 2 customers call each other, we'll do a link. So fantastic. Now go with this data set, go figure out how to make more money for your company. So actually, that's not a very uncommon scenario. Often you collect data first, and then you ask questions later. And you may not even know what's in the data, right? So if you apply conventional data mining tools, they're actually pretty nice. They say, oh, I'm going to tell you, these are the few things that you may want to look at, right? So, so actually, maybe very good, and they even give you a ranking. They say, oh, this is the first one, most anonymous, or most interesting, second interesting, but then they stop there. They're kind of like, oh, trust me. So I tell you, these are the 5 things you should look at, and that's it, right? But that's not really helpful because people don't really know whether they should trust the algorithm or not. But if on this side, if you apply techniques from human-computer interaction, or like apply even simple visualization techniques, like looking at the connection between the first 4 things, then you might see that there's actually a click. We call it a complete graph. So here only 4 nodes, but imagine this is 20 nodes. So that means 20 customers who call each other. Well, somehow either they are a close-knit family, or they're up to no good, like 20 people planning something and they keep calling each other. And also you provide a right interaction technique for people to expand the neighborhood of the 5th node. And then they see that, oh, this is actually the center of a star. So here in this network, that means it could be a telemarketer who call a lot of people, but those people don't know each other, right? So that's just a very simplified example of how the data mining techniques could help HCI techniques in terms of flagging things for them to look at, but that's not sufficient. It solved the hairball problem where we saw a very beautiful hairball. It can help pick up some of the interesting to look at, but then it doesn't really tell you why. So this is where the human-computer interaction, the human intuition, perception will be really helpful. So you would say that's probably a simplified example. Yes, exactly. That's a simplified example. We want to give you a more detailed example of what we actually, how do we apply these strategies. And so our goal is really to bridge these 2 areas, data mining and human-computer interaction, to develop scalable, interactive, and also usable tools for big data analytics. Well, if no one can use it, they don't know how to use it, it doesn't matter how powerful your tool is. So I'm going to show you a few examples of systems that we use these strategies. So the first system we call Visage is for to help people how to find interesting subgraph or subnetwork from a large graph. So you can think of this as a tool to help people get started in their analysis. So instead of having like a million billion node graph, so they can help you pick out the interesting thing where they might want to start. But only knowing where to start is not sufficient, right? You want to also know where to go next. That's where the next 2 set of tools, Apollo and Fastest. So I like to name things after myself. So that's not a typo. It is a 1L, Apollo and Fastest. So they help you go from the starting point to other areas, interesting areas that you may want to look at. Right? So let's start with the first one, the Visage one. They help people find an interesting subgraph or subnetwork within a bigger network. So to motivate it, I'll give you some example. Why do we even want to find subgraph or subnetwork, right? So here's the one, very interesting one. It's actually also my earliest data mining project to find the bad guys on eBay, so auction fraud. So people who get your money, but then they don't deliver item to you, very common, no problem. And the thing is that bad guys are really smart, right? So on eBay, for example, if you want to do this, we call non-delivery fraud, they get your money, don't deliver them. They will actually fabricate their reputation on eBay. So if you ever shop on eBay, you know next to your identity is a number, which is the aggregation between the positive feedback and negative feedback that you receive, right? So they try to create many accounts and then fabricate those accounts' reputation. More specifically, they will create 2 kinds of accounts. So one we call the fraudster identities, the other the accomplice identities. The fraudster's identities are the one that eventually trade with the victim. The accomplice identities, on the other hand, they look pretty normal. So they will trade with honest people, but then occasionally they will trade with the fraudster. Right, for some, we call it a heavyweight transaction. So things that would be like LCD TV, laptop computer, and so on. So the whole reason they want to do it is so that they can leave very strong feedback for the fraudster identity to boost their reputation. And of course, no real money really changing hands. I mean, the thing that they do need to pay is the eBay commission. But other than that, well, that's fine. So that means we have this structure. So that means before this fraudster identity, they want to defraud the honest people. They want to boost their reputation. And through these heavyweight transactions, actually this form what we call a network called near bipartite core. So bipartite because two types of nodes. It's a core because it's within the whole graph. And it's near because some edges could be missing. It's not the goal of the bad guy to really create a complete graph. It's just how the transaction appear to become a core. So you can actually find quite a few of them. So that means every one of these, so the red one are the actually reported one, our tool is able to flag the other that people don't know about. So we can find a lot of these actually on the eBay network. So where the edges will be transaction, nodes are either buyer or seller. So you can have a lot of them. So this is one example subgraph, kind of subgraph that you would want to find. So you would say, well, that's just in the eBay. So that's not true. So actually it's very common in many different problems, different settings. For example, you look at fake Yelp reviews. I'm trying to find fake Yelp reviews. You can also look at reviewers as the nodes in the graph and edges as you can link to a reviewer if they review the similar number of venues or same number of venues within certain time, then you can link them. And that's also suspicious, right? I mean, it's probably a real person controlling these accounts, and they, human beings have limitations. They need to act. They have time. They need to sleep, right? So they need to do the right thing and post them onto the account at the same time. So which is why you will see this kind of a new click also. And so we develop a tool that allow people to specify any pattern they might want, because you actually may not know. Sometimes it's click, sometimes it's nearby bipartite core, sometimes it's stars. So we developed a tool called Mage that allows people to find these patterns. And for example, here we're using a movie similarity graph. This is crawled from Rotten Tomato. So a little bit different setting. Oops, but I always show you a preview. So here the user can specify the subgraph pattern that they want to find, and then the system can find all the interesting thing from the whole graph. So it's able to find not just the exact matches, I would say also approximate match. For example, here the user may say, oh, I want to find 4 movies. One is action movie, one's drama, one is sci-fi, and the other one I don't really care about it. Right? And we would be able to find it. So this is an exact match, we call it. And at the same time, we also can help people find approximate match. And it's very important in analytics because often people don't really know what the eventual query might be. So they only start with something and then iterate. So that's a tool. But they also bring up a bigger question. So whenever you ask people to come up with a query, in this case, subgraph query, is it really easy for people to come up with that? Right? If you ever written SQL, you don't get it right in the first time. You need to do it a couple of times. And what's the current state of the art for people to do that? So it turns out, well, you also need to learn a language. For example, if you use graph database and you're Neo4j, you learn something called Cypher. And you want to find, say, a triangle pattern. In this case, we want to find 3 movies or action movies in 1980s. So conceptually very simple. And here's one exact match. If you want to write Cypher, you need to do this. If you want to do more complicated queries, even more complicated, right? More to write. So that's where the physics 2 comes in. So we want to make this process a lot easier and a lot less error prone so that people can more rapidly try things out. And so here are the more complicated example. Suppose it's data or graph about director, film, and actor. So director can add a movie if this director directed that film. So suppose what we want to find is, we want to see if there are any 2 co-directors who have, co-directed 2 films, and those 2 films cast the same actor. So that means, do they keep using the same actor, right? Do you actually find this? So if you're asking people to write this query, it's very likely that they will make a lot of error, and then they will also get nothing. So this is like a very common problem that you probably have seen every day. Whenever you use Google, the more search term you type, it doesn't necessarily mean you get more. You can actually get nothing. So that also happened actually even worse in graph because it's so complicated. So we introduced a new technique called graph autocomplete, which help people or prevent them doing this over-specification. So as they place nodes and edges incrementally to the visualization, we will tell them, hey, so actually it's impossible that you're going to get anything if you keep adding this like movie node or this director node. So we'll show them in the distribution to say, hey, it's not very common. So you can still do it, but likely you won't get that much, right? So if it's not possible at all, we'll tell them, hey, don't even do it. So something's wrong with your query. So that's a main interaction, the important interaction technique that we introduce, graph autocomplete, to help people prevent them from doing the over-specification. And in case you were wondering also, did I make that query up? So actually, no. So there you can actually find the Cohen brother, and they like to cast John Goodman quite a lot, and George Clooney also. So you can actually find that. Right? So that's a Visage tool to help people more easily find some graphs. Now, instead of writing Cypher query, now they can probably find some interesting places to start. But as I mentioned, just knowing where to start is not sufficient. Right? You also want to know where to go next. So that's where the Polo and Visage tool come in. So both of them share the common theme where try to combine machine learning and visualization to help people with this exploration, expanding on the initial investigation. So I talked about the Polo tool first. Right? So the very high-level problem that it's trying to solve is if the user say, I'm interested in particular node or particular subgraph in the whole graph, how to help the user find more relevant things, more relevant nodes. So here I'm showing a toy example graph of citation network. So edges here are citation links, nodes are papers. So let's say the user say, I'm interested in a paper about data mining in blue, another paper about human-computer interaction. So what are the other papers that I might want to read? Actually, it's extremely common. It's like finding related work in literature to read. So intuitively, you would expect that papers that are close to your initial starting point more likely to be relevant. So why is that? So if you read a paper, ever read a paper, you'll know that paper typically have related work section. We'll mention other work so I cite them because either they're good, either they're bad, but nonetheless they're relevant. So that means those would be these notes here. Those papers would be these notes here. And again, as you imagine further and further away, the related paper might cite another related paper. So that means the further away, the less likely, the closer, the more likely to be relevant. So saturation here encode relevance. So this is an intuitive way of thinking what might be relevant in your graph. So we leverage this intuition and develop a algorithm based on belief propagation to help people do this ranking. So rank nodes by relevance. And we call this a guilt by association approach. It just means that if I'm a bad guy, I know you, sorry, so you're probably also a bad guy. So guilt by association, spreading my guilt. So how does that work, right? So I'm gonna show you a demo of how Polo works. In the demo, we're trying to map out the sense-making literature or how people make sense of information. And as you may imagine, it would intersect many research areas. So what we're gonna do is actually just starting with one single paper. And the data that you're looking at is data that we crawl from Google Scholar. So about 80,000 papers, 150,000 citations. The note size here means citation. Number of citations, the bigger the note, more times it's cited. So we only start with one paper in the middle, here in black. It's called the Cause Structure of Sense Making. It's a seminal paper that studies how people make sense of information. What's the cause structure, what's the models, and so on. And we will start from just that, and then we'll find out what are the related research areas, such as information visualization, about search, collaborative search, or information management. So when we just start Polo, then, as I mentioned, just one tool, one node, right? So if there's one node, then it will show it in the middle, and on your right, that's where it will show the paper that either cited it or being cited by it. And at the bottom, you will see the exact same information you would expect to see from Google Scholar. So I'm gonna cheat a little bit here because I know the papers already, and we'll just skim the title a little bit and see, oh, there's one paper about information visualization, pretty general, it might be a good category to pick. There's another one about search, right? So I drag all of them into visualization. And then I want to say, well, since I have two starting nodes, right? So I'm going to try to label them, even tentatively. One I call search, the other I call info vis. Two things happen. One is the colors automatically assigned to them. And then the other is they also become the starting node of each of the two categories, the blue category and the red category. And then we can apply the guilt association idea, like spread the guilt from these two to their neighbors. And then that means the system, Polo, is able to give rank nodes. They can rank all the other. And if you look at them, just the title even, you will see, oh, these are about search, right? So a few clicks, we can get a few more example papers. So pretty good. So I can hide the rest. And now let's say, so why don't I go back to my original starting paper, right? The one in black, and I bring in the papers that directly link to it. So that means either citing it or being cited by it. So size here means citations. By default, they're sorted by the size. But since I have the two groups created, I said, well, why don't I just sort them by how relevant they are to the red group, right? So here after the, we call rank in place, we'll see that this one is about visualization. So it's good. So I'm also marked it as an example. And these two actually are also visualization systems, so they're also good. So something you might notice now more apparent here is there's a color change. Some notes become more saturated. So that's actually the way of Apollo how to surface the relevant information through the visualization to tell you, say, hey, maybe you want to skip the third note here, because based on the inference, we think the second and the fourth are more relevant. So this is a very subtle but effective way to tell the guide the user to say, I mean, if you're out of time, you might want to look at those first. Right. Of course, people can still do whatever they want, but here's a little bit of guidance. And we can follow the same strategy. And oh, so what are the other potential areas that I want to create? So this is information management. So I can give it another name. And that become an example. So that also means I can get suggestions for that as well. Right, so you can keep doing this. So this is actually a very natural thing that people would do anyways, whether you have the machine learning support in the background or not. People spatially arrange things when they look at graph. They group things, they tag things. But the very nice thing is that Apollo will have the algorithm running, leveraging all these actions that people would do and do the inference and surface it very effectively through the subtle saturation, color saturation. So actually people comment on the experiences like having a partnership with the machine. It's not like they're doing this labeling yes and no for the machine, but they're actually doing things that they want to do anyways. And now you have the addition benefit. And so the main thing that you saw it here is, you just saw it here, is that Apollo help users find more important things or more relevant things. So it's based on the traditional sense of relevance and importance or essentiality. But there are often cases that you don't just want to use importance, right? Importance mostly just tells you like the high, probably people that already know, right? So what about cases where people don't know yet, right? Things that people don't know yet. So that is where we developed the variation of Polo work called facets that uses the idea of surprise instead of importance to help people find things. So that means we'll help people find things that they may not know yet, but potentially interesting to them. So it's all our work that we just published going to be presented in May at a data mining conference. And you may say, why is it important? Well, very important because a surprise often leads to insight. Insight often means discovery people did not know about, but now they do. And how do you tell them, right? If they didn't even know about it, right? So that's why we are focusing on surprise. And in the graph analysis case, how do we leverage surprise? It's actually quite intuitive. So we would say a node in a graph is surprising if its neighbor is surprising. So as in a person, we'll say, how is that person special? Well, if it's surrounded by special people, so it's probably special. So technically, what does that mean? So that means we would want to look at all the nodes in the whole graph. And let's say we will look at all the, for each node, we look at its degree, like how many neighbors that they have. We do this for all nodes in the whole graph. And that will give you a distribution, which we show in gray here in the background. And now, whenever we want to look at one node, we just look at its direct neighbor. We call its EagleNet. So that means neighbor, other nodes that are directly connected to it, and also any edges that are among these nodes. So that means really you carve out the graph with just that one step away, one hop away neighborhood. And now, instead of looking at all the nodes in the graph, you just look at this small neighborhood. And you do the same thing. If we were looking at the distribution, now we also look at the distribution locally. We call this the local distribution. And we compare how different these two distributions are. Right? If they're significantly different, so that means probably this is surprising. If they're still more or less like the global thing, oh, probably it's the same. So that is how we, what the technical tool that we use to measure surprise. And of course, this we may not want to just use this alone. Maybe you want to actually combine it with importance, right? So that's what we do in facets, where we allow people to adjust how much surprise they want to do versus how much relevance they want to do, and then we can combine them. Right, so that's one of our latest work, and actually there are a lot more things that I would like to tell you, but out of time. And I think that this area of combining data mining, human computer action, or more generally combining human intelligence and also artificial intelligence these days, there's a lot of real value opportunity for explore. Because as you know, even like today, it's like deep learning, we're talking about self-driving car. There are cases that really cannot handle web. That's where you still need to rely on people to solve the problem. So we hope that by combining the best of both worlds, we can develop the best, the most perfect system available. So I will just stop here. Thank you very much.
So, thank you, Polo. We have time for a couple of questions. If someone would like to ask, please.
Is that fabulous paper citation tool available for public use?
Unfortunately, no, Polo is not available. So it was written in Java. So as you know, Java is very hard to run these days. So we're actually converting into a web-based version. So we hope to release it in the next few months, but currently not, unfortunately not, yes.
Very cool.
Oh, thank you.
Any other question?
I guess what technologies are you using to handle these very, very large graphs?
So the question was what technology will you use to handle large graph? So for a very large graph, so there are two ways. One, of course, is using cluster, like Hadoop and Spark. And the other, for the one that I mentioned very early on, like 37 billion edge. So that one is actually not very big in terms of graph structure. It's about 200 gigabytes. So at that time when I work on it, it's 2011. It can comfortably sit on a single machine. So just a disk. Yes.
All right, let's thank our speaker, Professor Polo, please.